Hello and welcome back to my lab. I've been a little sick lately, so you'll have to excuse my voice and also the occasional cough. But I'm starting to feel a little bit better, so let's get back to working on this. And I think the first thing I want to do is get the vertical belt hooked up and ready to go. It's going to be different than these guys because I actually need it to be an entire loop of belts. So because I need such a large belt, you can't really conveniently buy that, so I'm going to try to do what you're not necessarily supposed to do. I'm going to measure this out and then splice the ends of this belt together. That's usually very not recommended, but that's of course just means I can't resist. Thankfully, I have already tried this and it worked better than I thought it would. So what I've done here is I just took the two sides of the belt, I trimmed off the top of one and the bottom of another, and I used just regular contact cement to bond them together very firmly. And I kind of figured that would work, but not as well as it ended up working. So, I mean, I really can't budge this at all. So I think it's gonna be fine. So I wouldn't necessarily recommend it, but I'm actually kind of surprised how well this works. So let's go ahead and get the belt tensioner on the wall, this guy here, for the vertical axis. And then once we have that, we can measure out the belt and get that up there. All right, so now that that's on, we'll go ahead and measure the belt. So the belt's gonna start here, go up here, and then it'll go over here to be tensioned. So as I push this out, it'll add tension to the belt. Let's see how long it needs to be though. Okay, let's see. I marked where it needs to be spliced by cutting off that little tooth there. And then I'm going to unceremoniously just strip this whole thing down to the little steel core there. I'm just gonna wiggle it back and forth, and that should cut all the way down. There we go. So I'm doing this just to try to thin the end result so it's not quite so thick. So you can see the one I've done here. So it's more like this. So that way it's relatively thin, the splice. So I just lined up the teeth on this one here. So you just move from one to the next as if nothing happened. So on the other end, we'll just go about that same distance and we'll cut off the other side. All right, so now we have access to the steel, which might be why this works so well, because I'm going to sand this down a bit, and then the contact cement can come in direct contact with the essentially the spine of this belt. Okay, so now that I've got the surface scratched up, I'm just going to clean these up with a little bit of alcohol, and then I'm going to grab the contact cement. So if I really want to make sure something is completely oil-free, I like to use these Kim wipes. And then you brush the solvent over the Kim wipe, and that'll dissolve whatever it is that you want to get rid of, and immediately wick it up into the wipe here. And then you just keep going until it's dry. And that way you don't leave any oil residue to just stay put as soon as the solvent goes away. And now it's time for the contact cement. So this can be a pain to open sometimes. But the way this stuff works is that you apply it to both sides and you actually let it dry out a bit. And by a bit, I mean like for half an hour, 45 minutes. And then when you stick them together after that, man, they do not come apart. So this is really nice stuff. So once I clean off the brush sufficiently, and man, is it gooey. All right. So the goal is just to get a nice even coat, kind of puddle it on there. So in a way, we're kind of replacing the rubber that was in between these strands with the glue. And then of course this glue will stick to itself and they'll be bonded. So unfortunately now I have to just go do something else for half an hour while that sits there and dries. Okay, now is later, 45 minutes later or so. I went ahead, stuck down that. You can tell it's all dry and tacky. So now comes the tricky part, because these, you really, they tend to flail around and you really don't want them to touch each other. Because once they touch, they are stuck, which is kind of the point. All right, so the trick is to bring these together, but also to bring them together at the correct distance. So I'm going to use this guide to give me that pitch, the correct distance here. So this is a little bit tricky with only two hands, but I'm going to go ahead and engage these threads here, pull this guy back. Yeah, you probably can't see this, but it's just too tedious to do it any other way. And I'm just going to start kind of zippering it down. Just bring it together all the way down. Okay. And then I'm going to stick it together. So, okay. Looks a little weird now, but it's it gets better once you go ahead and clamp it. So I'm going to go ahead and put these plates in the vise and then this in between those plates. So I'll leave that for like 10 minutes and then these should be permanently affixed. And we're back. I left this overnight and just to make sure it cured all the way or set all the way. And it doesn't look quite as good as the first one I made in terms of alignment and all that, but I think it'll work just fine. And it's also equally very strong, stronger than I can break anyway. So now I actually have to disassemble a little bit of the mechanism in order to put this on. So I'm going to go ahead and do that because that'll get just a little tedious. So we'll go ahead and jump to having the belt on the machine so we can take a look at that. All right. Okay, so that's on now. I had to actually take off the motor mount and the pulley housing up there in order to get the belt on that the axles there. But now it should be good. It's a little bit of a pain in retrospect working with that, but this belt isn't going to break, so I won't have to do that again, probably. Just gotta get all the slack out here, up over there. And this one works the same as the others. I've just got a screw that slides that guy out. And I'm just gonna kind of slide it through as I tighten it so the slack or the tension distributes. Okay, I think that's good enough. think that works. I took the plate off. You'll see why in a second, but just ignore that for now. I think these belts just work, so that's actually kind of cool. I really expected to have to finagle with these a bit more. Turns out we'll have to finagle with other stuff, as you'll see in about 2 seconds. But this is done. Let's move on. I have what I'm calling the pen pusher, the first prototype of it, and it's not looking promising. This is meant to go up and down with this solenoid, but the problem is that this design, ignore that, with this design has too much stiction. I was going to cut this out of aluminum to have even more practice on the mill, but I've done enough milling on this project, so I don't really care to make these tiny little pieces. So rather than cut this on aluminum, I tried it on the new printer. I've got that super cheap SLA printer just to see if I like SLA printing, and it's pretty cool. This one's not that accurate, so the tolerances are quite wobbly. I think it's like 0.1 millimeters too big, which is just not really good enough for this delicate a mechanism. The whole thing torques around, and then there's a bunch of stiction, which means that the solenoid that's supposed to have a nice easy push, just once it pushes down, it won't come back, and I don't think that's going to be a reliable mechanism, and that's going to be really critical to the functioning of this whole machine. So I was hoping I could just put that on and play with it, but I think I might have to either redesign this to have less stiction with these parts, or I'm going to have to rethink the whole thing and build it differently. I could probably replace this solenoid with a DC servo, like the kind that people use in RC planes and stuff. That would be a little bit easier to do. That's probably what I'll do, but I'm going to think about it. Let's just move on to the rest of the electronics while I'm thinking about this.
You're 0.1 millimeter too big. That was a fat joke, son.
And here we have the electronics panel. So everything is going to go in here. I've got all this stuff in a pile. So we'll probably explain this a little bit more as we go. But first things first, I got to lay everything out in the panel so I know where that the screw holes are going to go. And then I can put that on the mill and cut the screw holes. It'll make more sense when you see it. After that, I'm going to have to cut some actual larger holes for wire glands and stuff to get the wires through. And yeah, all of it's going to make more sense when you see it. So maybe we'll just get to it and you'll see as we go. Firstly, I'm going to undo all the test wiring that I used to get the system up and running. I like the wiring for the most part, so I'm going to go ahead and put the final labels on for these wires, and that's just going to be labeled according to the terminal block that I pulled them from. I'm going to also add some ferrules, because pretty much whenever I'm wiring, I'll go ahead and add ferrules to just about everything. It just makes life so much easier. And that's this metal sleeve you see going on there. You just crimp it onto the end, and it takes what's normally a stranded mess and makes it one nice metal tube. Then I'll go ahead and cut some DIN rail and start laying out the entire panel, all the components. Once I have an idea of where I want all the holes, I can just go ahead and take it to the mill and start cutting the holes. I have to be careful when tapping thin sheet metal like this. It can be really easy to go very sideways. This thing you see here is actually the relay I'm going to use to interrupt power to the servos, and that'll be useful in the e-stop circuit that I'll talk about later. Here I'm adding some holes for wire glands. I'll talk about those in a sec. Then I'll add some holes to the front panel for an Ethernet bulkhead. And also the e-stop. Here's the actual wire glands I was talking about earlier. They're a convenient way of adding strain relief to wires that are leaving the panel, but also if the panel were sealed, they would maintain a seal. This panel is not sealed, so it doesn't matter. So now the panel is ready to get rewired again, and I made some changes since the original test wiring. So I think what I'm going to do is just go ahead and rewire this up, make some changes, and then we'll talk about what I did once I'm done. So we'll just cut back once I've got all the wiring back together. All right, and it's pretty cramped in here. Normally you would use a much bigger panel, and you would use what's called wire ducts, little ducts with holes in it so you can stick the wires through. That leaves things much cleaner, and you can see what you're looking at much more easily. And you'd use terminal blocks instead of these guys, but this method allows me to use a much smaller panel, and right now that's the priority for me. If this were like a factory or something, you really wouldn't care how big the panel was. You would care primarily about how clean it is inside and how easy it is to work with. Here, I am optimizing for other things. And I'll just give a basic overview of the wiring here for those that don't really want to get into it technically. There's not going to be a power switch on this. If it's plugged in, then it's on. And the power is going to route to the 24-volt power supply, which is going to power all the logic circuitry and everything like that. And the e-stop button here is wired both to the e-stop signal that goes into the controller, as well as it's actually going to run to a relay that will cut the, well, we'd usually call that high voltage power, but it's not very high voltage, the power supply to the servo motors so that they can't actually run. That way you can cut power to the servos so that they're safe, but you've still got all your logic circuitry running. That's kind of the preferred method of doing that. Of course, I've got a circuit breaker in there as normal. It's all step-in direction, and because these are clear path motors, the control loop is inside the motor itself, which is a little bit different than normal industrial motors. Then this thing is just going to all be controlled through Ethernet to a laptop or something. So I've got a bulkhead Ethernet connector here that's going to go through to the controller. So ideally this thing will just never be opened. It's just going to stay closed like this. You plug it in when you need it, and keep the e-stop on until you want to actually run the machine like a normal industrial machine. And that's essentially everything. So let's just go put it up on the wall. Here it is. everything is plugged in just nicely. Box went on the wall pretty easily. Everything is hooked up. Let's see. So I went ahead and tuned these axes, and turns out, due to the lack of rigidity, as I kind of figured was going to happen, we can't run these axes very fast at all. So, but they're still going to be way faster than I could draw by hand. We'll get into that in a sec. But essentially, the way this is going to sit here and look is that you're just going to have this box on the wall. We'll use a laptop to just plug in using this Ethernet cable here, and you'll have direct control through the CNC software from CS Labs, I think it's called. We'll get deep into that in the next episode, but I just want to show you it running since we did all this work. So with it all tuned and the distances are calibrated to be square and everything, we can go ahead and run it. Of course, I don't have the pen pusher up here because, like I said earlier, that's not going to work. So I'll have to redesign that. But I can probably just, hold it as it moves, and we'll get an approximation of what things will look like. So first of all, let's just do what's really hard for a human and easy for a machine: a circle. I'll bring this to the center here, and then make a nice big circle in the center. All right, so we're kind of just limping it along here for now, but we have programs that'll run this automated later. So I'm gonna go ahead and move this to kind of the center. And, about there. Maybe a little bit back. There we go. And a little bit down. Oh yeah, that's great. I think I'm gonna start at the top of the circle I wanna make. Let's see, so that's probably 700 millimeter diameter circle. So I'll type in a 350 millimeter radius circle, and we'll just see what it makes. This will execute the command. I'm just gonna stick the marker in. Obviously that's not where the marker is gonna go, but it's a convenient spot for now, so I can go ahead and just press it against the thing. I wouldn't necessarily advise putting your hands on a new machine, but we've tested this a bit more than you've seen, so I kind of trust it now, and it can't go that fast, so here we go. We're going nice and easy. I need better markers. I'm gonna have to buy a bunch of markers. There we go, one nice little circle. Real slow like. We'll be able to go a lot faster than that later. But now I will get this out of the way. And there we go. So we'll be able to program it from there. We've got some code to generate more efficient G-code paths. The G-code is the kind of program that runs this thing. We'll get into all of that in the next episode, so I don't have to hold the thing myself. We're gonna have to redesign the pen pusher. I've actually already been working on that a bit, and I've got that mostly finished, so it shouldn't take too long to get that finished up, and then we'll 3D print the components and get it mounted on here. And with all that said, thank you for watching, and we'll see you next time.